Behavior of functions on intervals. Hello, everyone. Let's begin our session on the behavior of functions on intervals. To start, let's recall that in our previous subsection, we established the fundamental definitions of what maximum and minimum values are, essentially, the highest and lowest points a function can reach. However, it is important to understand that a function does not always actually reach these values. Whether a function attains a maximum or minimum depends heavily on two critical factors. First, we must consider the nature of the function. This refers to how the function behaves, for example, whether it is constantly climbing, constantly falling, or fluctuating. We will dive deeper into this when we discuss monotonic functions in the next slide. Second, we have to look at the type of interval, or the domain, that we are considering. As we will see in the upcoming sections, there is a significant difference between a closed interval, which includes its endpoints, and an open interval, which does not. Throughout this tutorial, we will explore exactly how these two factors influence the existence of extrema, which is the collective term for maximum and minimum values. Monotonic functions. Now that we have established that the nature of a function and the type of interval determine where maximums and minimums occur, let's examine a specific type of behavior known as monotonic functions. A function is described as monotonic if it is either strictly increasing or strictly decreasing across its entire domain. To be strictly increasing means that as the value of x increases, the value of the function, f of x, always increases as well. Conversely, strictly decreasing means that as x increases, the value of f of x always decreases. This leads us to a very important rule for these types of functions. If a function is monotonic on a closed interval from a to b, it cannot have any peaks or valleys in the middle of that interval. Because the function only moves in one direction, the maximum and minimum values must occur at the boundaries, which are the endpoints of the interval. To make this clearer, let's look at a real-world example of constant growth. Imagine a plant that grows at a steady rate every day for 10 days. In this scenario, the height of the plant is a strictly increasing function of time. Let's break this down using a step-by-step analysis. First, we identify the interval. The time interval here is a closed interval from 0 to 10 days. Second, we identify the behavior. Since the plant only grows and never shrinks, the height function, f of t, is strictly increasing. Third, we determine the minimum. The plant was at its shortest at the very beginning of the observation. Therefore, the minimum value occurs at t equals 0. Finally, we determine the maximum. The plant is at its tallest at the very end of the 10-day period, meaning the maximum value occurs at t equals 10. While monotonic functions are straightforward because they only move in one direction, many functions are more complex. In the next slide, we will explore the extreme value theorem to see what happens when a function is continuous, but not necessarily monotonic. Continuous functions on closed intervals. Now that we have discussed monotonic functions and how their extrema are found at the boundaries, let's broaden our scope to look at continuous functions on closed intervals. First, let's clarify our terminology. A closed interval is a set of values that includes its endpoints, which we denote using square brackets. From a to b alongside this, we have the concept of continuity. A function is said to be continuous if its graph has no breaks, jumps, or holes over that specific interval. Essentially, you could draw the curve without lifting your pencil from the paper. This leads us to a cornerstone of calculus known as the extreme value theorem. This theorem states that if a function, which we will call f, is continuous on a closed interval from a to b, then the function must attain both an absolute maximum and an absolute minimum value at least once within that interval. You might ask, why is this guaranteed? It is because the function is continuous and the interval is closed and bounded. This means the function cannot escape toward infinity, nor can it approach a certain value forever without ever actually reaching it. Because it is constrained within these boundaries and has no gaps, it is forced to have a highest and a lowest point. To illustrate this with a real-world scenario, consider the temperature, T, of a city over a fixed 24-hour period, from midnight to midnight. We can represent this time frame as a closed interval from 0 to 24. Let's analyze this using the criteria we just discussed. First, temperature is continuous. It does not jump instantly from 20 degrees Celsius to 30 degrees Celsius. Rather, it changes smoothly over time. Second, the time period is a closed interval, strictly bounded between t equals 0 and t equals 24. Therefore, according to the extreme value theorem, we can conclude that there must be a specific time during the day when the temperature was at its absolute maximum, the hottest moment, and a specific time when it was at its absolute minimum, the coldest moment. While this theorem provides a guarantee for closed intervals, it is important to remember that this may not hold true if the interval is open. We will explore exactly how that changes the outcome in the next slide. Functions on open intervals. Now that we have discussed how continuous functions on closed intervals are guaranteed to have absolute extrema, let us shift our focus to a different scenario: functions on open intervals. First, let us define our terms. An open interval is one that does not include its endpoints, which we denote using parentheses as the open interval from a to b in practical terms. This means that while the variable x can get infinitely close to a or b, it can never actually equal those boundary values. This leads us to a very important rule. Unlike the extreme value theorem we just covered for closed intervals, a function defined on an open interval may not have a maximum or minimum value at all. This is especially true if the function is strictly increasing or strictly decreasing throughout that interval. To illustrate this, let us look at a simple example: the function f of x equals x, considered over the open interval from 0 to 1. Let us analyze the minimum value first. As x gets closer and closer to 0, for instance, if we pick 0.1, then 0.01, and then 0.001, the value of the function also gets smaller. However, because the interval is open, x can never actually be 0. Therefore, there is no single smallest value. No matter what tiny number you choose, I can always pick an even smaller one that is still closer to 0. Now let us apply the same logic to the maximum value. As x approaches 1, taking values like 0.9, 0.99, and 0.999, the function value increases. But again, since x cannot actually equal 1, there is no largest value that the function ever reaches. In conclusion, for the function f of x equals x on the open interval from 0 to 1, there is neither a maximum nor a minimum value. This highlights why the type of interval is just as critical as the nature of the function itself when determining the existence of extrema. Key takeaways. Now that we have explored the different types of functions and intervals, let's consolidate everything we've learned into this summary table. This will serve as a quick reference guide for you to determine whether a function has a maximum or minimum value. First, let's look at the first row regarding monotonic functions. As we discussed with the example of the growing plant, if a function is strictly increasing or decreasing on the closed interval from a to b, it cannot have any peaks or valleys in the middle. Therefore, the maximum and minimum values will always occur at the endpoints, a or b. Moving to the second row, we have continuous functions on a closed interval from a to b. Recalling our discussion on the extreme value theorem and the daily temperature example, the key word here is guaranteed. Because the function is continuous and the interval is closed, it is mathematically certain that the function will attain both an absolute maximum and an absolute minimum value. Finally, let's consider the third row. Any function on an open interval from a to b, as we saw in our analysis of the function f of x equals x on the open interval from 0 to 1, the lack of endpoints means the function can get infinitely close to a value without ever reaching it. Consequently, in this scenario, a maximum or minimum value may not exist. Please take a moment to study this table carefully, as these distinctions are crucial. In the next slide, we will discuss some common mistakes students make when applying these rules, so you can avoid those pitfalls in your exams. Common mistakes. Now that we have covered the theory, let's wrap up this session by discussing some common pitfalls. It is very important to be mindful of these 3 common mistakes to ensure you don't lose marks on your exams. First, be careful not to confuse open and closed intervals. As we discussed in the section on open intervals, students often assume that if a function is strictly increasing on the open interval from 0 to 1, the maximum value must be the function of 1. However, this is incorrect. Because it is an open interval, x can get infinitely close to 1, but it can never actually equal 1. Since 1 is not part of the domain, the function never actually reaches a maximum value. Second, do not fall into the trap of assuming that continuity alone is enough to guarantee a maximum or minimum. While the extreme value theorem tells us that continuity on a closed interval ensures extrema, this does not apply if the interval is open. For example, consider the function f of x equals x cubed over the interval from negative infinity to positive infinity. Even though this function is continuous everywhere, it continues to increase and decrease forever, meaning it has no absolute maximum or minimum. Finally, a very frequent error is ignoring the endpoints. When you are searching for the extrema of a function on a closed interval from a to b, it is common for beginners to only look for the critical points where the derivative, f prime of x, equals 0. While those points are essential, you must also check the function's values at the boundaries. X equals and x equals b, as we saw with monotonic functions. The absolute maximum or minimum often occurs exactly at these endpoints rather than at a peak or valley in the middle.